So now let's consider a case of 3D crystal. And in 3D crystal, we have a function which is periodic, but predict not just in one direction, but in all direction. So we can translate it by a Bravais vector, like in this fashion. So the Fourier series can be written for 3D crystal as rho of r equal to summation over vector in reciprocal vectors in three-dimensional rho of g vector e I g dot r. So you should note that this is the scalar product. It is a scalar product, and this is a vector, and this is vector in nature. This is vector in nature. Okay, so in quantum mechanics, e this expression is a plane wave concept. So G are discrete vectors or points in a reciprocal space. So what is the expression of G in case of three-dimensional crystal? So imagine if direct lattice has primitive vectors a1, a2 vector and a3 vector. So this is the primitive vectors for direct lattice. So we can represent not necessarily of same length, which are perpendicular to each other, like in this fashion. These primitive vectors are perpendicular to each other. So in that case, can be factorized. This plane wave can be factorized. Harmonic function can be factorized along the direction of along the x, y, z directions. So if the primitive vectors in the direct lattice are perpendicular, the reciprocal lattice vectors can be given by this expression. So here HKL are integers which play the same role of n in one equation. So HKL and L plays the same role in case of n in case of one equation. So the main key point is that the main key point is that the reciprocal lattice is related with direct Bravais lattice, and it depends only on the periodicity, and it doesn't depend on the basis. So if we have a crystal of some Bravais lattice but different bases, then we have the same reciprocal lattice. So the value of Fourier coefficient rho j is given by the integral over the primitive cell. So we can write it as rho j equal to 1 by Vp integral over the volume of the primitive cell rho for E minus I g dot r dot dr. So one way to define all the reciprocal vectors are all the wave vectors of the plane waves which have the same periodicity of the direct crystal. So wavelength is either equal to the period or some multiples of the period. Um, now let now let's demonstrate. Now let's demonstrate that rho of r equal to this expression is periodic. We have to prove this thing. So let's try again by applying the same concept of the previous lecture. We are going to translate. Let's translate this function by. Let's translate the function by n. So we can write it as or we can further solve it and we can write it as so if this is periodic, then ei of gn must be equal to 1, must be equal to 1 so we can write okay, so this can be taken as an implicit definition of wave vectors. So if a1, a2 or a3 are not perpendicular, we can use this relation to calculate the value of g vector. So here we can write e power I of g dot n can be further simultaneously can be written into this thing. Okay, so this is the periodic plane wave. So this is the periodic plane wave. So here here n is the combination of the primitive vectors of Bravais lattice. So if we change the Bravais lattice, we also change the reciprocal space vector, that is g. So in that lattice, it is n1 a1 plus n2 a2 as we have seen in the first lecture. Okay. So in that lattice, index are n1, n2, and n3. And the most general expression for G vector is done by considering the prime vectors a1, a2, a3 of that lattice of different length, and we can write the expression of G as this in this fashion. So it's K. So in reciprocal lattice, index are HKL, which are integer coefficients. So how to find B1 how to find B1, B2 and B3. So in order to find B1 we can use this expression, cross product of A2 and A3 vectors divided by modulus of A1 vector scalar product of A2 cross A3 vector. So basically this is the denominator is the volume of the primitive cell. This is the volume of primitive cell. Done. And in a similar fashion we can calculate B2 by this expression, that is A3 cross A1 vector divided by the volume of the primitive cell, and B3 vector is equal to A1 cross A2 vector divided by the volume of the primitive cell. So if A1, A2 and A3 are perpendicular, then if A1, A2 and A3 are perpendicular, then A2 cross A3 is equal to A3 cross A1 equal to A1 cross A2 equal to 1. So primitive vectors of reciprocal lattice is, so we can say that the primitive vectors of the reciprocal lattice is equal to 2 pi bn vector, 2 pi b2 vector and 2 pi b3 vector. Here h, k and l are Miller indices. Now let's jump to the properties of the reciprocal lattice. So the first property is that the first property is reciprocal lattice is a Bravais lattice in the inverse length space, which is called reciprocal space, Second property is reciprocal lattice of the reciprocal lattice is the direct lattice. The third property is, so since the reciprocal lattice is a Bravais lattice, so we have the primitive vectors. So we have the primitive vectors 2 pi b1, 2 pi b2 and 2 pi b3 vector, which constitute a unit cell, in this Bravais lattice. So volume of the primitive cell in the reciprocal lattice, so volume of the primitive cell in reciprocal lattice is equal to 2 pi cube upon Vp. Here Vp is the volume of the primitive cell, is the volume of primitive cell in direct lattice. In direct lattice. Now coming to the fourth property. We need to plot. Now consider a given Bravais lattice and a family of crystallographic planes with Miller indices HKL. Now let's take the square lattice. Now let's take a square lattice. So take a usual square lattice. Crystallographic planes are a set of parallel planes which pass through the points of the Bravais lattice, like in this fashion. Yeah. So these are the crystallographic planes which pass through the points, which passes through the points. And these are called family of crystallographic planes which are parallel and are at same atomic distance from each other. So the more the planes are closer, the less dense are the points in the plane. So there will always be a vector. Suppose if you're going to join in this fashion. Okay. So there will be always a vector GHKL which are perpendicular to these planes, where so the vector is represented by something like this. This is perpendicular to this plane, so this vector is G of HKL, so to these planes where the Miller indices will be the same as obtained by intersecting the axis and so on. So it always exists GHKL perpendicular to the planes, which means if you have a direct lattice and suppose you look family of planes and these indices are exactly obtained by this method. Now the last property is the distance between the planes in the family of planes is given by this equation. So we have to take the smallest, we have to take smallest reciprocal vector perpendicular to the plane, that is the value which have the smallest Miller indices. So this marks the completion of the reciprocal lattice. So for now, thank you.